Okay, for this final part of this essay, I'm going to talk about more of osmosis. Osmosis is very similar to diffusion, except it's purely just dealing with water. Osmosis is the movement of water across a selectively permeable membrane from an area of high concentration to an area of low concentration. So basically, the water is moving from the side with lower solute concentration to the side with higher solute concentration until it reaches equal concentrations or equilibrium. So I drew out this picture. I'm not sure what this thing would be called, but it's kind of just a little container. Right here, I'm putting a semi-permeable membrane that's only permeable, or in other words, only lets water cross through it, but no solute. So on both sides, I'm going to put equal amounts of water. And then on this side, I'm just going to throw in some solute. Let's just say I put 4. But on this side, I decided to maybe just double it. I'll just throw in a lot more. Oh, the idea is that this side has more solute than this side. Okay. So with osmosis is going to want to basically equalize those ratios of solute to water. So since this side has a lot more solute in comparison to water than this side does, the water is going to want to move from this side over to that side, because they're like, holy cow, there's so much solute here, we're outnumbered. Well, it's like, okay, we'll send help, we have extra people. Goes through that permeable membrane, and what it does is creates this difference in the amount of water in there until it reaches a state of equilibrium. So it reaches a state where pretty much the ratio between the water and this the solute is equal to this side, and it creates a change there. So pretty interesting. Cool. So that's osmosis for you. Just a quick little lesson there. Now we're going to talk about osmolarity. So osmolarity, so there's different ways we can measure concentrations in different solutions. So let's actually talk about molarity first. So this one's should be familiar to you if you've taken chemistry. So it's molarity, we represent it with capital M. Moles of solute. So moles is just basically a number that represents molecules just a number of molecules. It's 6.02 times 10 to the 23 molecules. It's just a huge number, so we just reference that to just 1 mole, just to simplify things. So like this could be, for example, let's just use NaCl for these. So NaCl, this is 1 molecule of NaCl, or let's just say this is 1 mole of NaCl. This is going to be our solute. We measure that in liters of solution. And our solution is our solvent, which would be our water in this case, plus the NaCl. So just like the whole cup. If we had a cup, it includes the water with the NaCl in there. Cool. So this is just one way we measure concentration. What it doesn't account for is ions or dissociation of ions. So when sodium or NaCl is placed into water, it can actually separate nicely into 2 different things, into a sodium ion and a chloride ion. So now there's pretty much like the double amount of things inside the solution. It's not just like one thing, like NaCl, it stays together, it's happy like that. It's going to separate. So now there's just more influence of different things within the solution. We call this in chemistry at least like a von Hoff factor, which accounts for this dissociation of ions. More complex ions like glucose, this doesn't dissociate very nicely. So it just stays as this. So that would have like a von Hoff factor of 1. 1 ion that's really making a difference in the whole thing, 1 particle. But this one would have a von Hoff factor of 2 because it's dissociating into 2 different particles or ions. So it's going to have pretty much double the effect on things. So to account for this happening, this dissociation, we have osmolarity, which I believe is just os like that. And that equals moles, or sorry, that's number of particles per liter of solution. So hopefully that's clear what the difference there between molarity and osmolarity. Okay. Now we're going to talk about osmolarity versus tonicity. So when we're talking about osmolarity, we're pretty much describing the total solute concentration of a solution compared to that of a cell. So a lot of the time we're comparing things between the cell and a solution. So each thing has their certain, I guess, concentration of solutes or different things, different osmolarities. Normally the cell has an osmolarity of 300 milliosmoles inside of it, right? This is just the number of concentration or number of particles it has per liter. So that's its concentration there. But solutions can have different types of concentrations. It could have more particles in it, or it can have less. When our concentration is equal, when it has the same number of particles in the solution as it does compared to the cell, we call this isosmotic there with an S right there. When the concentrations are equal, I'm just going to do equal. This is concentration right here. Okay. Now, when it is, when the solution, so it's really just a point of comparison, really. When the solution has more particles per liter, or a higher concentration or higher osmolarity than the cell does, so let's just say it had 400 milliosmoles. Okay. Then this would have a higher concentration than the cell. So to kind of describe that reference, we call it hyperosmotic. Hyper just means more. Perfect. And then to describe when the concentration is less than the cell, so we have 200 here and then 300 here, comparing the solution to the cell, we would call the solution hypoosmotic to the cell. This is a hypoosmotic relationship. Okay, perfect. So that's describing more osmolarity. It's just describing the total solute concentration of a solution and comparing that to a cell. Now we have tonicity. Tonicity gets a little bit more tricky, but it's not too bad. Tonicity describes more so how a solution affects the volume or shape of the cell due to the concentrations there. So now with tonicity, so with osmolarity, we're kind of just looking at, we just care about the concentrations of both the cell and the solution before anything even happens. But as we talked about earlier with osmosis, this changes things. It's going to cause movement of water from the solution to the cell and vice versa. So with tonicity, we can have different types of kind of terms for tonicity. We can have isotonic. This is where, so we're going to go like this, going to have a little bit bigger of a container. Like that. So we have our cell, that's 300 milliosmoles. Okay, so in this isotonic solution, it has the same concentration of non-permeable solutes as the cell. So non-permeable, I mean, is just like the solute's not going to make its way into the cell pretty much. So this one has 300 milliosmoles, and then this one the solution has 300 milliosmoles. Like that. So it'd also be isoosmotic, just because they have the same number of concentrations. But since there's the same number of concentration, the water's happy. It's like, no, there's no reason for me to move over there, no reason for it to leave the cell. Nothing's going to happen to the cell. It's just going to stay the same shape and size. Now let's say that This one has, the solution has 400 milliosmoles. So more particles per liter of solution than the cell. This would cause the water to be like, holy cow, they're getting outnumbered in the solution. We gotta go help them. So the water will move outside the cell into the solution. And this would make it a hypertonic solution. And the effect that this would have, and hyper just means pretty much a higher concentration outside the cell than the inside. But this is more talking about the effect. Water will leave the cell and go into the solution, so it'll cause it from going like a nice, pretty cell like that to being kind of like, it's like all dehydrated and gross. So that'll happen in a hypertonic solution. Now we have, let's pretend here. Okay, so now we have our third scenario. So now we have it where, let's say, so the cell has 300 milliosmoles. Let's just say the solution had 150 milliosmoles. So kind of review from osmolarity, this would be a hypoosmotic solution because it has less solutes than it does in the cell when you're comparing the two. So since water's like, oh, sorry, that was the same example. I think I went backwards right there. Let me just maybe cut that out. Okay. Anyways, okay. So this is it's a 150. So let's just say we have less concentration inside in the solution than the cell. So since it has a less of a concentration, oh no, it's right. Okay, I'm right. Okay, so this has less of a concentration, this one has more. So it's like, crap, the water in there is getting outnumbered. We have so much extra water per thing. So now we can go into the cell with the water. This will cause a swelling of the cell. It'll go like, and it'll even sometimes burst. I don't know how to draw that, but that'll happen there. So this would be a hypotonic solution. So there's less solute as compared to that inside the cell, so the water will move into the cell. Okay. Hopefully that makes sense there. Now it gets kind of weird with, sometimes you can get it where a solution can be isoosmotic. Let's see if I spelled that right. Osmotic. But it could be hypotonic. And you should be thinking like, what the heck? That doesn't make sense. If it's the same concentration, why would the water want to move? Because they're all happy, right? Well, there's some solutions that are, or solutes that are permeable. They're able to cross that membrane. And one example is dextrose. So we have 5% dextrose is our example that we're going to use. This is just pretty much glucose, a glucose solution. And if you remember from bio, glucose is metabolized by the cell to create ATP. So it uses glucose as a source of energy. And 5% dextrose is equal to 300 milliosmoles of particles. So when you have this in here, you're like, okay, like that looks the same. Why would, so there, this is isoosmotic, but why would it be hypotonic with the solution compared to the cell? The reason for that is that with dextrose, since the glucose is able to cross that membrane, it's permeable to that membrane, it will make it in there, so it'll go into the cell here, and then it's going to be metabolized by that cell. So it's going to keep using that, and it's going to create a concentration gradient with that. Because if it's going into the cell and it's being used up, then there's going to be less of the glucose inside the cell than there is in the solution. So I'll just keep driving that to keep going because it's going to keep getting used up. So I'll keep pulling it in. But then we'll run into a problem that it's pretty much like all this was used up. So now we're at like 0 milliosmoles in the solution, and then we're at 300 milliosmoles of non-permeable solutes. So now it's like, holy cow, we are so overpowered with solute in this side inside the cell, we need help from water. And the solution is like, we don't have any solutes in here, so let's go send all our water. So that'll follow the glucose. And it'll cause the cell to swell and possibly lyse. So this is just an explanation of osmosis, osmolarity versus tonicity, the effects on the cell with different types of, like when you're talking about tonicity, and how a solution could be isoosmotic, but also hypotonic. And that will be it for this exam essay.